Okay, in this video, I go over the homework solution for the project management problem. The problem is taken out of the Stevenson book, chapter 17. I think it's problem 7. We're given some activities and some predecessors. We're also giving some time estimates, and we're supposed to draw the network in part A and answer the likelihood of meeting a due date in problem B, or part B. So always have a start and finish node. If the activities listed don't have predecessors like A, B, and D, then you want to link those to the start node. And then if you don't see the activities listed in the predecessor list, for example, E, I, and G are not listed, they're not listed in the predecessors, those are going to be the ones that are linked to the finish. You can sort of tell when you draw it, but that's this is what we have. So we have essentially three paths through the system. I promise you, it's much easier. I can create much more complicated. In real life, there's more complicated projects. This is not something you want to do paper and pencil. You want to have some software. Excel is probably not the best tool for this, but Excel is a good teaching tool. It teaches you some basic formula writing, and it does allow us to do some what ifs. So the first thing I did was calculate the average, which is a weighted average, 1 part optimistic, 4 parts most likely, 1 part pessimistic, divided by 6. You can calculate the variance. Pessimistic minus optimistic squared divided by 36. The formulas for the earliest finish and the earliest start are a formula that you can copy down. The earliest finish is always equal to the earliest start plus the average time. The latest start is equal to the latest finish minus the average time. So we can copy these formulas down always. The rest of them, not so much. I've got a start node, and I put that at 0. After that, the activity A, since its predecessor is the start node, I reference it from the earliest finish column. Same thing for B. C's predecessor is A, so I reference A. D's predecessor is back to the start node. E's predecessor is the C node, all the way down to the finish node, and the finish node has 3 predecessors, so you have to take the maximum. Once you do the forward pass, you do the backward pass, and the first thing I do is make the latest finish equal to the earliest finish. Then after that, I look at the network, and I see that I, its successor, is finish, so I reference this. H successor is I. G successor is finish. You work your way all the way up until you have the start activity, and it has 3 successors, A, B, and D, so you take the smaller of those. Once we have those 4 values, we can calculate a slack value. The slack is just the bottom numbers minus the top, or the latest finish minus the earliest finish, or the latest start minus the early start, either way. And then an activity that has 0 slack is a critical activity. So I've got some conditional formatting to see that it goes through D, F, and G. So this is the critical path. It's the longest path. The definition of critical path is the longest path. If I did some what ifs on this, let's say that activity A, which right now is not a critical path, and the average time to complete this is, or the average time to do A is 6 something. What if I could throw resources at this and cut this down to 1? So look what I'm going to do. I'm going to overwrite. I'm going to override that 6 with this 1 and just hit enter. What is it going to do to the critical path? Nothing, because it's not on the critical path. So there's no reason to throw resources to try to shorten activities that are not on the critical path. But if I go to activity D and shorten it, I'm going to shorten it from 12. I'm going to shorten it by 1. Look what happens to the critical path. It went down by 1. So when you cut down the shortest pole in the tent, the top of the tent is brought down. Now there's a point where another critical path, another path may become critical. In this case, this is what happens. When I shorten that activity by 1, now we have 2 critical paths. We have the one that goes initially through A, that is along with the one that goes through D. So you have 2 longest paths. So and again, that's good information. That's good information when you're trying to go out and trying to reduce or crash activities. Once we have this, I can calculate the average. The average is just one of those numbers. You would never ever try to have a due date equal to the average because the likelihood of meeting that is 50%. So don't quote the average. If the average time to complete the project is 21.5, don't say, hey, I'll be done in 21.5, because you're only going to be right half the time. You want to pick a due date that's further out there. The variance, standard deviations we can't add, but we can add variances. So what I did was sum the variances of the activities on the critical path using the sum if function. Took the square root of that to come up with the standard deviation of the overall project. So I have a project centered at 21.5 with a standard deviation of 1.34. If you look in the book, we can assume that that project time follows a normal distribution. And so if I put in a due date of 24, the likelihood that I can meet that is pretty high. So that's what you needed to do for the problems. Just to go into, I think Part D talks a little bit about how to crash if you have dollars to crash. So if I had to pick these activities, and this is what the investment would cost to crash those, and I have 20 grand, which activities should I crash? Well, the only ones that I should initially is only consider either D, F, or G. Those are only, so the only ones I want to look at is this one and these 2. And all you're trying to do is which one is the cheapest to crash. Well, it's activity F. So if you were going to crash one, just to reduce this by 1, activity F is what you would be focused on because it's the cheapest one to crash. Okay, that should be enough information to do the homework as what we covered in class. I've got a bonus for you. I'm going to post this solution because I have developed a template for you that you can use on the test, you can use later, you can take and use this later. A template, it doesn't have too many activities you can put in, but you no longer have to go through and calculate the earliest start and the latest finish on your own. All you have to do is put in a 1 if that activity is a predecessor. So for activity A, its predecessor is start, so I put a 1. Activity B, I put a 1 and D. Activity C's predecessor is A. So once I complete this, I don't ever have to go and mess with this again or this. It will change it. It will do it automatically for you. So if I would start from scratch, I'll just show you. Activity A's predecessor. Activity B has a start. A is C. Activity E, I can't remember. Activity E is C. Activity F is D. Activity G is F. H, its predecessor is B. I's predecessor is H. And then finish has 3 predecessors, E, I, and G. E, I, G. And there you go. It automatically, dynamically calculate these. There's some math that's hidden in rows. You can certainly go play and look at that. I'm not going to go into the detail of what happens. You can either just use it as is. Again, it's limited. It can only solve up to those many activities. If you have a bigger project, it won't be very useful unless you expand this. But if you want to expand it, have at it. Thanks.